Usually when we talk about a software failure, there's a very specific, theater to it.
Yeah, definitely a hater.
Right. Like there's this expectation of a visible, undeniable crash. We're talking about an error log just vomiting stack traces all over your screen, or a blank white page where an app should be.
Or a database timing out.
Exactly. Or a giant red X stopping your deployment pipeline dead in its tracks. It's loud. You look at the code, you track the stack trace down to, line 42, you find the null pointer exception, and you just point your finger directly at the syntax error.
It's a fundamentally binary world, historically speaking. I mean, the code either compiles and runs, or the compiler yells at you. The test suite passes, or it fails.
Right. Broken or not broken. It's a clean, almost comforting reality, in a way.
It is comforting. We like our problems to be highly visible and easily localizable.
We really do. But then you step into the world of AI-generated code, into this rapidly accelerating era of autonomous development, and suddenly that comfort completely vanishes.
Oof, gone.
Yeah, gone. We're no longer looking at clean binary failures. We're looking at a landscape that is incredibly, dangerously murky.
Which is a profound shift in the engineering paradigm. We're moving from failures of syntax to failures of intent.
Failures of intent.
Right. And a failure of intent doesn't throw a compile error. It often looks like, perfectly functioning software right up until the exact moment it does something catastrophic.
Welcome to the Deep Dive. Today, we're exploring a massive tectonic shift in how software is being built, and honestly, how it's currently failing right under our noses in absolute silence.
It really is silent.
It is. For you listening, whether you're a senior engineer trying to manage a team of developers who are suddenly using AI for everything, or a product manager wondering why feature velocity isn't matching up with feature stability.
Which is a huge problem right now.
A massive problem. Or even if you're just someone fascinated by how artificial intelligence is rewriting the nature of complex work. This is a conversation about the very foundation of how we build and trust digital systems.
We are pulling our insights today from a really rigorous piece of research published by Rooted Layers AI Systems, grounded in research.
Yes, Rooted Layers.
The post is titled, "The Specification Surface is the New Source of Truth." And throughout this deep dive, we'll naturally be referring to this source material simply as the post. It acts as a fantastic lens for understanding this entire transition.
Our mission today is to unpack the mental models and the bigger hidden patterns behind a very popular trend called vibe coding. And we're going to compare that to what the post calls spec-driven development.
Yeah, and we need to explain exactly why this matters right this second.
Absolutely. Because as AI agents generate code faster than any human being can possibly read it, we're facing a massive crisis of governance. We're going to explore why the code itself, like the actual lines of JavaScript or Python or Rust, is no longer the authoritative source of truth in a system.
And what specific artifacts are stepping up to take its place?
Right. Okay, let's unpack this. Before we get to the solution, we really have to deeply diagnose the exact moment this current AI coding paradigm breaks down.
The failure point.
Yeah, the failure point. And according to the post, it breaks down at a very specific, historically sacred ceremony, which is the code review.
The pull request.
The pull request.
This is where the modern, quiet failure of AI coding really manifests. I want to paint the picture the post provides because it's a scenario playing out in, thousands of repositories right now.
Oh, every single day.
So a pull request is submitted by an autonomous AI agent or maybe a developer heavily relying on a coding assistant. The human reviewer opens it up. They look at the the lines of code added and removed, and the code looks entirely plausible.
Right. It uses the company's internal styling. The variables are named reasonably. The tests pass. The AI has even generated a polite, articulate summary explaining what files it changed to implement the new shopping cart logic.
It feels like a successful transaction.
It totally feels great.
But if you look closer at the systemic impact, the reality is much darker. A subtle database schema was renamed during the generation process.
Uh-oh.
Right. A critical retry branch in the network logic simply evaporated.
Just gone.
Just gone. And the truly terrifying part isn't just that these things happen. I mean, bugs happen. The terrifying part is that no one on the human team can point to a maintained, authoritative statement of what this feature was actually supposed to preserve in the first place.
There's absolutely no record of what assumptions were settled before the AI started churning out logic.
Exactly. And no record of what behavior was explicitly defined as out of scope. The code is entirely visible to the reviewer. They can see every single character. But the authority behind the code, the reason it exists in that specific architectural shape, is completely invisible.
It's just missing.
The engineering team is sitting there reviewing a downstream artifact, but the controlling intent, the actual constraints, those vanished.
Where did they go?
They were left behind in an ephemeral private chat window between a developer and a large language model.
Wow. Yeah, it's like finding a fully built house on your property one morning, but the architectural blueprints burned down in the process of building it.
That's a great way to put it.
Like, sure, the house stands, the door's open, you can turn on the faucet and water comes out. So you think, great, the AI built me a house.
Right. Job done.
Job done. But you have absolutely no idea why a load-bearing wall is placed exactly where it is. You have no idea if the builder remembered to insulate the pipes behind the drywall, or if they just, skipped it because the statistical probability of needing insulation wasn't high enough in their training data.
Yeah, the training data didn't emphasize insulation, so it's not there.
Exactly.
Yeah.
You're left walking through this finished house, forced to reverse engineer the architect's original intent just by staring at blank drywall.
A useful way to think about this is as a total collapse of governance. We often treat these AI hallucinations or dropped features as technical bugs, but they aren't. They are governance failures.
Governance failures.
This is the fundamental flaw of what people call vibe coding.
Ah, vibe coding. We hear that term everywhere now.
Everywhere. And vibe coding is this highly romanticized workflow where you just chat with an AI, give it some vague atmospheric vibes about what you want, like build me a sleek authentication flow. And it spits out an app.
And it looks like magic.
It looks like magic, but it relies entirely on misplaced trust. As the post points out, the deepest failure isn't that the AI might make a mistake.
Everyone makes mistakes.
Right. The deeper systemic failure is that the human's intent remains entirely informal until that generated code becomes the only object the team treats as real.
Because once that generated code is merged into the main branch, it becomes the new reality. It literally becomes the physics of this system.
Yes, and the second that happens, you are trapped. Because when something inevitably breaks a month from now, every diagnostic question has to be reconstructed from symptoms.
Oh, that sounds like a nightmare.
It is. Like, why did the agent choose this specific database indexing strategy? Which performance constraint was it actually trying to satisfy?
And you just don't know. You might have a prompt transcript saved somewhere, or a vague JIRA ticket, or some private design choice that only lived in the original developer's head. But none of those things can govern the system unless they are durable, reviewable, and repairable.
So, because we can no longer rely on the code itself as the memory of the system's intent, because it's being generated and overwritten at machine speed, we need a new artifact to take its place.
We absolutely do.
We need a new set of blueprints that don't burn down. And this leads us to the absolute core concept of the post, which is the solution to this governance crisis. It's called the specification surface.
This is the critical pivot. The post formally defines a specification surface as a written surface that gains operational force.
Let's really dig into that phrase, operational force. That sounds heavy, almost legal.
It does sound legal.
What exactly gives a piece of writing operational force in a software environment?
It gains operational force because the system is designed to reject deviations from it.
Reject deviations.
Yes. It is actively controlled and maintained. The post is very specific here. A specification surface has operational force when it is typed, linted, validated, trace-linked, interpreted by a runtime environment, or compiled into test suites.
Okay, so it's not just a text file sitting around.
No, not at all. It is the stable, immovable artifact against which the AI-generated behavior is constantly automatically checked.
And the post makes a fascinating distinction that I want to highlight. It explicitly states that the syntax is secondary.
Yes, very important point.
Whether the surface is written in YAML or Python or heavily structured English Markdown, that doesn't matter as much.
Yeah.
The decisive property is governance.
This fits a broader pattern we're seeing across complex systems engineering. Loose prose remains loose prose regardless of how insightful it is.
Right.
You can have a readme file in your repository that is full of brilliant, deeply considered architectural advice, but it does not become a control plane just by existing in the directory.
Just because it's in the folder doesn't mean the code listens to it.
Exactly. A one-off chat prompt where you told the AI to, ensure the payment gateway is secure does not become a source of truth just because it preceded the code generation. The surface only matters. It only possesses operational force when both the software system A and D, the human team, can act on it, enforce it, and fail a build if it is violated.
But wait, I have to challenge this premise.
Go for it.
If we take a step back and look at the history of software development, particularly the Agile movement, isn't this just a regression back to writing massive requirements documentation?
Ah, the waterfall argument.
Yeah, because we have been telling developers to write specs and docs for decades. And the historical reality is that they constantly rot.
They do rot.
They go out of date the absolute second the code changes. The Agile Manifesto literally prioritizes working software over comprehensive documentation for this exact reason. So how is this specification surface any different from the old waterfall method of throwing a massive markdown file into a repository, calling it a spec, and watching it become instantly obsolete?
I'd argue that confusing a specification surface with static waterfall documentation is the single most common trap engineering teams fall into right now.
Really?
Oh, absolutely. The Post explicitly warns against the lazy version of this claim. Throwing Markdown into a repo and calling it a source of truth is a delusion.
A delusion.
The fundamental difference between passive documentation and an active specification surface is the presence of an automated control loop.
The control loop.
If a Markdown file is ignored by the runtime, meaning the AI can generate code, the code can compile, and it can deploy to production even if it violates every single rule written in that Markdown file, then yes, it is just documentation, and it will rot.
It has no teeth. It's just a suggestion box.
Exactly, a suggestion box. The mechanism of control is what matters. If a failure in the system automatically pushes back into a required revision of that file.
Like it forces you to update it.
Yes, if the AI agent's output is programmatically checked against the constraints in that file before a pull request can even be opened, then it is a governed surface. Authority does not come from the romance of writing your ideas down. Authority comes from the maintenance loop.
That makes a lot of sense.
The Post states this clearly. You need enough specification to remove consequential ambiguity, but you must have enough enforcement to make architectural drift painfully visible.
I really like the factory mold analogy for this.
Oh, yeah, the factory mold.
A specification surface isn't a picture of the plastic toy you want the factory to make. A specification surface is the heavy steel mold itself. The AI-generated code is just the hot plastic being poured into it.
Right.
If the plastic toy comes out with 3 arms instead of 2, you don't spend hours sanding down the plastic toy to fix it. You go back and remachine the steel mold. The mold has operational force. The toy is just a downstream artifact.
That is a perfect mechanical translation of what the Post is arguing. The code is the plastic. It is ephemeral.
Okay, so we've established what a spec surface is and how it functions as a control plane. But why is this so incredibly urgent now?
Because of velocity.
Right, because we've always had rotting design docs. We've always had technical debt. Why is this suddenly an existential crisis for engineering teams? And here, the Post moves us from the theory of specifications to the raw reality of AI operating at machine speed.
The old software problem is familiar to anyone listening who builds things. Requirements drift, design documents rot, and eventually the code itself becomes the only artifact anyone actually trusts to tell them what the system does.
Which is a bad place to be.
It is. But AI coding raises the pressure on this old problem to an extreme breaking point. The reason is velocity. Implementation can now appear faster than intent can be reconstructed.
Because an AI can spit out 10,000 lines of code across 50 files in 30 seconds.
Exactly.
If you don't have a rigid specification surface, you are immediately drowning in implementation with absolutely zero intent to anchor it.
This brings us to the concept of spec-driven development, referencing work by researcher Deepak Babu Piskala. Spec-driven development forces an inversion of the traditional hierarchy.
An inversion.
It treats specifications not as an afterthought and not as documentation, but as binding contracts. The code is merely something that implements, verifies, or derives from that contract.
And to really drive home what happens when we don't have these contracts, the Post brings in a brilliant empirical study by Camillo Ciccone-Sartori.
That study is fascinating.
This study looks at coordination failure. Specifically, it looks at what happens when multiple AI agents attempt to work together on a single code base.
The mechanics of the Ciccone-Sartori study are incredibly revealing. They set up an environment where multiple autonomous coding agents were tasked with independently implementing different parts of the same software class.
Okay.
Now, to test the value of intent, the researchers manipulated the shared specification. They systematically stripped detail away from it, reducing full, rich doc strings down to bare, minimal function signatures.
So they essentially starved the AI agents of intent. They said, here's the name of the function and the inputs, but we aren't going to tell you the larger purpose or the constraints.
Yes, they degraded the specification surface, and the results were stark. When the specification is stripped down to these weak, bare signatures, the integration accuracy of two agents working together falls off a cliff.
Just tanks.
Tanks completely. Interestingly, a single agent working alone on the entire problem degrades much more gracefully.
Here's where it gets really interesting. What this implies mechanically is that AI agents cannot vibe with each other.
No, they cannot.
If you have a single human developer, they can hold a massive amount of unstated context in their head. A single AI agent might maintain a coherent internal state or latent space during one localized chat session. But when you introduce multiple agents, they cannot read each other's latent spaces.
They cannot infer unstated shared design decisions from fragments of code. Let's look at the mechanism of that failure. Agent A assumes a user ID should be handled as a string because the weak spec didn't specify.
Makes sense for Agent A.
Agent B assumes the user ID is an integer. They both write perfectly functioning, locally optimized code, but when you integrate them, boom, the type mismatch destroys the system. Without a strong central specification surface explicitly dictating those contracts before generation begins, multi-agent systems just end up building completely incompatible puzzle pieces.
They're guessing in a vacuum. And the recovery result in that study is even more important than the failure itself, right? Because they didn't just break the system, they tried to fix it.
Right. The researchers introduced a conflict detector, a post-hoc inspection tool to identify these structural mismatches after they happened. Think of it like a very advanced linter.
Did it work?
The detector worked perfectly. It found the integration errors. But, crucially, the conflict reports themselves did not fix the problem. The agents could not reliably repair the system just by looking at the errors.
Wow. Find the symptom didn't restore the lost intent.
Not at all. The only intervention that recovered the performance of these multi-agent systems back to the single-agent baseline was restoring the full, rich specification.
That's huge.
Better post-hoc inspection is not enough. Diagnosis only explains where the break appeared, but the specification is what carries the shared decisions that prevent the break from becoming normalized in the first place.
You know, if you are listening to this and you work in a traditional human software team, you actually already know this pattern intimately. You know about API contracts. You know about acceptance criteria and open API Swagger docs.
Yep, the pain is the same.
You know that if the front-end team in New York and the back-end team in London do not rigorously agree on the exact JSON payload of an API beforehand, it is going to be an absolute disaster when you try to integrate 6 weeks later.
The specification gap we are seeing with AI is just the machine speed version of that exact same software problem. Separate workers, whether human or algorithmic, do not reliably converge on unstated decisions. AI agents just make the catastrophic cost of weak surfaces much easier to see because they generate plausible-looking, fundamentally incompatible work so much faster than human organizations can reconstruct the intent behind it.
Okay, so we've seen how theoretical multi-agent systems crash and burn without rigid specs. But how are actual seasoned human developers surviving this shift in the real world? Because the empirical reality of how professionals work is catching up to the theory.
To understand the reality on the ground, the post dives into a fascinating ethnography paper by Huang, Reina, Lerner, Xia, and Hempel. It's titled, "Professional Software Developers Don't Vibe, They Control."
I love that title.
It's great. This study actually observed how experienced senior developers in 2025 are utilizing coding agents in complex production environments.
And the title alone really shatters the marketing illusion of AI coding. These senior engineers are not just sitting back, sipping a latte, typing "build me a billing system" into a prompt and letting the AI take the wheel.
Far from it. Experienced developers absolutely use agents for speed. The velocity gains are real. But they aggressively, almost obsessively, preserve their own agency over the system's design and implementation.
How do they do that?
The researchers found that these professionals do not start with code. They plan extensively before implementation, they supervise the outputs closely, they validate the changes locally, they rely heavily on atomic version control, and crucially, they artificially limit how much work an agent is allowed to do in a single pass.
They construct a very tight sandbox.
Yeah.
They're constantly forcing the AI to pause so they can inspect the work against their mental model.
Yes. They're relying on their hard-won domain expertise to decide exactly where autonomous agents are suitable and where they are far too dangerous. They absolutely do not treat the agent's output as an autonomous, unquestionable authority.
So what does this all mean for you? Think about your own workflow for a second, whether you're coding or writing or analyzing data. When you use an AI tool, are you just blindly accepting the output because it looks grammatically correct and it felt incredibly fast? Or are you building what the Post calls infrastructural skepticism into your process?
That phrase, infrastructural skepticism, is the hinge of this entire philosophy. The Post points out that the slogan, "Don't vibe, they control," isn't just an attitude.
Right, it's not just a mindset.
No, the mechanism of control is the takeaway. Vibe coding is fundamentally a source of truth error. It asks the large language model to carry the intent privately, hidden deep within its latent space, and then asks the resulting generated code to stand as the public record of that intent.
It is exactly like asking a magician to keep the secret of the trick in their head, but expecting the audience to maintain the illusion long after the magician has left the building. It's unsustainable.
That is a brilliant way to phrase it. Professional control actively moves the burden of intent back into inspectable artifacts. Plans, specifications, integration tests, architectural constraints, reviewable diffs, execution traces.
Artifacts you can actually see.
Control has to live somewhere that the rest of the human team and the rest of the algorithmic agents can actually read it, parse it, and audit it.
Okay, so if experienced developers are demanding this level of rigorous control, how are researchers actually building the tools to give it to them? Let's move from the philosophy of control to the actual implementation layer. How do we build these specification surfaces so they are truly operational?
The Post synthesizes several cutting-edge research papers to show how this works mechanically in practice. First, there is a seminal paper by Martin Monperus called Bootstrapping Coding Agents. The specification is the program.
Okay.
This paper demonstrates what I would call a controlled inversion of the software development lifecycle.
A controlled inversion. Break the mechanics of that down for us. What exactly is being inverted?
So, in a traditional development setup, human intent drives the writing of code, and that code creates the program.
Makes sense.
In Monperus's framework, the stable authoritative artifact is a highly compact, heavily structured specification. That specification is actually used to generate a bespoke AI agent tailored specifically to that task.
Wait, it generates the agent itself.
Yes. Then, that newly minted, highly constrained agent uses the same specification to generate the actual code implementation.
Wait, so the specification surface acts as the DNA that creates the builder, and then it acts as the blueprint that guides the builder.
Precisely. The specification becomes the durable object of the system. The code implementations that the agent spits out are treated as purely downstream products. They're essentially disposable.
It's disposable code.
If the implementation diverges from what you wanted, say it fails a security check or introduces a bug, the repair target is not the code. You do not just manually open the generated Python file and hack in a hotfix.
Which is what everyone does right now.
Right. But here, you fix the specifications, instructions, or constraints, you regenerate the agent, and the code updates automatically.
That is wild. It treats the code as entirely ephemeral. It takes my factory mold analogy from earlier to the extreme. You don't even look at the plastic toy. You only ever interact with the steel mold.
It's a profound shift in where human labor is applied. And then you have papers like Natural Language Agent Harnesses by Pan et al. And Agents PEX by Wang et al.
What do they add?
These papers take this logic and move it directly into the execution structure of the AI system itself.
How so? What does an execution structure look like when it's governed by a spec?
They take vague human intent and forcefully channel it into an auditable runtime process. Instead of an open-ended chat, they use programmatic harnesses that explicitly define decomposition, meaning how exactly a massive task is broken down into atomic, verifiable steps.
So no more build me a whole app prompts.
No. They define strict roles for different specialized agents. They manage memory and state explicitly outside of the LLM's context window. Agents PEX even introduces a typed workflow language.
A typed workflow language. So
Yeah.
we aren't just writing paragraphs of English anymore. We are writing logical structures.
Right. It explicitly dictates branching logic, loops, state management, checkpointing, and tracing. You define the exact pathway the agent must walk.
It sounds like the entire paradigm of managing AI is undergoing a massive industrial shift.
It really is.
We are moving from treating AI like a really smart intern who we give a vague, inspirational pep talk, hey, go build a payment gateway, make it look nice, and let me know when you're done.
Which never works out well.
Never. To handing that same intern a highly specific, typed, algorithmic checklist that is literally wired to an alarm system that goes off the millisecond they skip step 3.
The mechanism of enforcement is what changes the paradigm. And papers by Rehan on test-driven AI agent definition and Jin on fast-trick show how this discipline is applied right at the interaction layer.
Okay, how so?
They show that a natural language product specification isn't just passive text. It can be automatically parsed to generate both visible tests and hidden tests.
Hidden tests. You mean the AI is being graded during generation without knowing the exact answers it's being tested against?
Yes. The system parses the specification, generates unit tests, hides them from the agent's context window, and then lets the agent generate code.
Wow.
It forces the LLM's prompt refinement and tool usage to happen against a verifiable objective standard rather than its own internal hallucinations of success.
So it can't just trick itself into thinking it did a good job.
Exactly. As the post argues, the point here isn't that making things stricter always magically improves the AI's raw coding ability. The point is that the right specification surface makes the behavior inspectable.
Inspectability is key.
Formality only earns its place in an engineering workflow when it gives a software team something they can test, audit, and repair. It is not about making coding harder. It is about making autonomous behavior governable.
Okay, so having a rigorous type checklist and hidden tests sounds fantastic. But we all know human nature.
Oh, yes, we do.
If no one enforces the checklist, it just becomes a wish list. And this brings us to what the post identifies as a massive ubiquitous trap that almost every engineering team is currently falling into: the danger of passive instruction files.
This is perhaps the most actionable insight in the post for teams working right now. It is incredibly common practice today for teams to create files in their code repositories called, agentfest.md or claude.emd or copilotinstructions.md.
I've seen a million of those.
They dump project guidance, architectural rules, naming conventions, and security standards into these markdown files, hoping the AI coding assistant will read them, internalize them, and behave.
And let me guess, it doesn't work. The AI just happily ignores rule number 14 because it found a faster way to write the function.
It is a trap because it relies on a false assumption. The assumption that providing an LLM with more context automatically produces more control.
Context does not equal control.
Exactly. A long instruction file, just sitting there passively in the file system, is incredibly weak. It easily becomes stale. It fills up with contradictory rules over time as different developers add to it. Or the AI simply ignores it because its attention mechanism gets overwhelmed by the sheer size of the context window.
So how do we actually fix that? How do we make the AI care about their agents.md file without turning it into a massive bottleneck?
The post highlights a brilliant paper by Rishabh Sharma called Context Cov. This paper provides the exact mechanical bridge from a passive instruction document to an active, enforced invariant.
Okay, what does context conf do?
Context Cov actually extracts the natural language constraints written in those markdown files and programmatically turns them into executable checks.
I want to make sure I understand the mechanics of this. It reads English rules like, do not use external APIs for date formatting, and it somehow turns that into a code test that runs in the pipeline.
The mechanism is fascinating. It parses the natural language and maps it to different types of validation. It might create shell shims, it might generate abstract syntax tree, or AST queries.
Let me pause you there for the listeners. AST queries, abstract syntax trees. Basically, it's a way of representing the grammatical, logical structure of the code, right?
Yeah, that's a good way to describe it.
So it's not just doing a dumb keyword search for the word date. It's actually analyzing how the logic branches and whether a specific disallowed function is being called anywhere in the execution path.
I take that a step further. It understands the relationship between the components of the code. So Context Conf uses AST queries to verify architectural rules, but it doesn't stop there. For rules that are too nuanced for rigid structural checks, it actually uses LLM-based judgments.
How does an LLM judge a rule in a pipeline?
It isolates the evaluation. In the deployment pipeline, a separate independent LLM is spun up. It is fed the specific rule from the markdown file, say rule 4, and it is fed the diff generated by the coding agent. It is prompted simply to evaluate, did the agent violate rule 4? So it's a completely separate process.
By isolating the generation from the evaluation, the passive document transforms into a source of active, continuous invariance. And if the agent fails those checks, it reveals not just that the agent made a mistake, but it provides observability.
Observability into the rules themselves.
Right. It might reveal that the instruction surface itself is ambiguous, stale, or drifting.
So the post offers an operational test for anyone listening who wants to know if their team has a real specification surface or just a fancy rotting document. Here is the test. If a file can change what an AI agent is actually allowed to execute, if it changes what memory state persists between sessions, if it actively gates what outputs are allowed to merge into the code base, then it is a specification surface.
Yes, that is the defining line.
If it just describes the project so a new human hire can read it on their first day, it is just documentation.
The distinction is absolute. Documentation explains. Specification governs.
But I have to push back on the reality of implementing this.
Go ahead. How do teams realistically keep these operational surfaces from becoming overwhelmingly bloated? If every single architectural preference has to be a strict invariant, if every English rule has to be converted into an executable AST query or an LLM judgment call in the pipeline, don't we lose the flexibility and the sheer velocity that makes large language models so powerful in the first place?
That's the fear, yes.
Aren't we just reinventing the absolute worst, most rigid, bureaucratic parts of 1990s waterfall software development?
That is the practical burden every engineering manager has to navigate, and the post addresses it directly. Teams cannot specify everything. That is a fool's errand. They have to decide which surfaces actually deserve the cost of authority.
Deserves the cost.
Yes. The goal is to keep these specification surfaces short enough that a human being can still read and audit them, structured enough that a parsing machine can interpret them, and close enough to the actual execution that violations cause immediate localized pain.
Localized pain.
You do not write a 500-page spec document. You lint your instruction files to keep them concise. You validate your typed workflow files. You test the prompt behavior. You apply governance selectively, specifically targeting the areas where AI implementation is moving much faster than human intent can track.
Okay, so let's say we do all of this. We have an active operational specification surface. We've written our tight, concise rules. We've generated our hidden tests. We have context graph extracting our markdown into active invariance.
Perfect.
But what happens when the generated code inevitably still fails or misbehaves? Because it will. Hallucinations happen. Edge cases exist. How do we use this governed surface to actually recover the system?
This brings us to the crucial downstream side of the hierarchy, traces and audits. The post cites some really innovative work here, like Agent Pex, Agent Fixer, and a paper by Rashid titled From Fluent to Verifiable.
Fluent to verifiable. I love that phrase.
That's very descriptive.
Because LLMs are incredibly dangerously fluent. They sound completely confident and articulate, even when they're hallucinating a library that literally doesn't exist.
The fluency is exactly what lulls reviewers into a false sense of security. If you rely on outcome-only scoring, meaning you just check if the final generated code compiles and passes basic tests, you will completely miss procedural violations.
Right.
An AI might produce a polished working output, but the trace of how it got there might be horrifying. It might have used a deprecated library, violated a strict data compliance policy, or completely ignored the architectural constraints to brute force a solution.
It just duct taped it together behind the scenes.
Polished outputs are incredibly dangerous if the relation between the claim, this code works, and the evidence this code followed the rules cannot be reconstructed.
So we need an audit trail, the AI's thought process.
We need traces. These systems act as an evidence surface. They capture the telemetry of the agent's execution. They evaluate the trace to tell the human team, did the execution actually respect the specification surface at every step? Or, conversely, did the specification surface fail to say enough to prevent the AI from taking a dangerous shortcut?
And what happens if it did take a shortcut?
Agent Fixer, for example, uses validation checks and trace comparisons to do automated root cause analysis. It takes those failures and turns them into direct refinement pressure on the specification itself.
But the post is also very careful to point out the limits of this entire framework.
Right.
It does not claim that natural language is suddenly perfectly replacing code. or that generated code somehow stops mattering because the spec is so good.
Oh, not at all. Generated code absolutely still matters. It is the raw executable material of the system.
Yeah.
It carries the actual runtime bugs, the latency bottlenecks, the memory leaks, and the security exposures. It carries the long-term maintenance cost and the real-world consequences for the end user. A serious engineering team must still review the code.
But the nature of that review has fundamentally permanently changed. The post argues we have to redefine the pull request entirely. The PR review must now happen upstream of the diff.
It's a total reorientation of the reviewer's attention. A team that only treats the code diff as the whole truth is just reviewing symptoms. They are looking at the burnt house and trying to guess what the blueprints look like.
So let's lay out the new workflow. For you listening, the next time you are reviewing a pull request generated by an AI, whether it's Copilot, Cursor, or an autonomous agent, the post suggests you need to ask a completely new set of questions before you even look at the lines of code.
3 specific questions.
Question 1. What specific maintained surface governed this agent's behavior? Question 2. What trace evidence shows that the agent's work actually conformed to that governing surface? And question 3. What missing constraint or decision needs to be added to the specification surface before we ever run this agent again?
And if the answer to those questions lives only in a transient chat transcript you had with an AI yesterday, then, as the post perfectly puts it, the system is still running on atmosphere.
Running on atmosphere.
It is entirely ungrounded. If, however, the answer lives in a maintained artifact that can be read before execution, actively checked during execution, and systematically repaired after a failure, then your team finally has a true source of truth. That transition from atmosphere to artifact is where AI-assisted software work finally becomes governable.
So let's synthesize this incredible journey we've been on today. We started by dismantling the illusion of the perfect pull request. We looked at the quiet, systemic failure of vibe coding, where the code looks completely fine on the surface, but the driving intent has vanished into the ether.
We did.
We established that the era of relying on the code itself as the sole memory of a system's intent is rapidly ending. Vibe coding is a temporary, highly fragile state of misplaced trust.
And the future of complex engineering belongs to those who govern AI through maintained, typed, and executable specification surfaces. We looked at how theoretical multi-agent systems literally crash without shared, rigorous specs, and how real-world seasoned developers are already building infrastructural skepticism into their daily workflows.
They don't vibe, they control the input.
We explored the actual mechanics of making those surfaces operational, moving from passive markdown documents that rot in repositories to active invariants powered by AST queries and LLM pipelines that actually gate the deployment.
We learned that the code is no longer the sole source of truth. The specification is the mold, and the code is just the plastic.
Ultimately, the frame here is not some utopian vision that natural language is the new code. The common property of all these surfaces, whether they are written in YAML, structured Markdown, or Python tests, is governed authority.
Governed authority.
They are maintained surfaces that systems can read, that automated tools can check, that humans can review, and that system failures inevitably push back into revision.
So for you listening, I want you to look at your own repositories and your own workflows tomorrow morning. Look at the way your team is utilizing AI. Are you relying on atmosphere? Are your architectural blueprints burning down every single time you generate a new feature? Or do you have a governed surface? Are you actively inspecting the intent of the system, or are you just endlessly chasing the symptoms of its hallucinations?
It is a critical, necessary shift in engineering mindset. We are moving from managing the endless volume of output to rigorously governing the constraints of the input.
And I want to leave you with a final, slightly provocative thought to mull over. Something building on all this incredible research, but pointing even further into the horizon.
Yeah, what is it?
If AI systems continue to accelerate at their current pace, if they can soon generate hundreds of thousands of lines of code in seconds based entirely on our rigorous operational specification surfaces, will human developers eventually stop reading code entirely?
That's a huge question.
What happens to the software industry when our only job, our sole value add, is writing, reading, and debugging the specification surface itself?
And further.
What happens when those specification surfaces become so incredibly complex and interconnected that we need an AI just to write the specs for the AI?
Layers upon layers.
Are we just moving the murky waters one layer higher up the abstraction stack? You might have the perfect house and you might have saved the steel mold. But what happens when human beings can no longer read the language the blueprints are written in?